Alright, what up everyone? Here we go on the Mod 11 review packet. So the very first question here is talking about the daily clock-in times for the last work week. So, like 7 a.m., a little bit before 7 a.m., that's kind of what they're talking about here. And we need to calculate first the mean clock-in time for Doc. Because we have all of the entire last work week, we are talking about the entire population. So actually this X bar is not even the right letter. It should have been this little mu guy, little U with a little thing attached to it. In order to calculate this stuff, the mu, we're actually going to use the X bar in the calculator. The calculator only reports the X bar, but they're actually the same exact thing. But in order to get this in the calculator, we're going to have to enter into a list first. So entering this into a list in the calculator, you're going to hit second first, and then the stat button. I lied to you, don't hit second first. You hit stat, and then you hit edit. After hitting stat edit, it looks like I already have a list in here, so I'm going to need to clear that off. So I'm going to scroll up to L1, hit clear, and then enter, and this clears off the list. Now I need to type in each one of these numbers in a single list. So 7, 6.9, 7, 6.8, 6.7. Once I've typed in all of these numbers into the list, I'm going to go ahead and hit second mode to quit out. Get back to our main screen. I'll hit statistics again. Scroll over to the right for calculate. Hit enter for one variable statistics. And then go ahead and hit enter a couple of times. And you will get this guy right here. So our mean is 6.88. And the standard deviation is this guy right here. It's that little sigma character. That is going to be 0.1166. You don't really need that many decimal places, but hey, whatever. This is what we are equal to. It now asks us to compare the means and standard deviations of the two sets. I guess they're missing an S there. And describe what these values tell us about the daily clock-in times of Doc and Happy. It appears that Doc clocks in earlier on average compared to Happy. So Doc is earlier than Happy. I'm not going to write these down. Just go ahead and listen to it. Doc is earlier than Happy. Furthermore, Doc is also more consistent than Happy because his standard deviation is lower than Happy's, which is 0.279. So in other words, most of Doc's times are around the 6.88, off by about 0.1 or so. So he goes up to about 7 and down to, about 6.78 or so. Whereas Happy here sometimes comes in even earlier than Doc, all the way down to 6.7 and lower. Whereas he also clocks in way later as well, up to 7.3. So that's kind of what we're talking about when comparing and contrasting here. You just want to talk about where the center is and how they are spread out. So there you go. Find the mean standard deviation and sample standard deviation of the following set. Unfortunately, we just have to do this entire thing in a list one more time. I'm moving over here so it's easier for me to type in. Hitting all the buttons again, quitting out, you hit stat, edit. Got to clear off this list by scrolling up, hitting clear, hitting enter, and then type in all the numbers. 1, 2, 2, 2, 4, 5, 6, 7, 8, 8, 10, 12, 12, 12, 13. Quit out. Stat, calc, one variable statistics, enter, enter, enter. Boom. Gets us this value. We have the mean. So the mean could be using X bar or mu depending on what situation you're in. Either way, it's going to be 6.93 repeating. Your standard deviation, just like in the previous question, is that bottom number with the sigma, 4.05. Should have a little X on there. 4.057. And the sample standard deviation, the SX is right above it, is 4.199. I guess 4.200. As a reminder here, the sample standard deviation is used when they ask you for a sample, whereas the sigma is used for the entire population. Moving on to this next one, asks you to fill in this bell curve about these chihuahuas. The weight of an adult chihuahua is normally distributed with a mean of 5.4 pounds. That means this middle value is 5.4. with a standard deviation of 1.1. The markings here on this normal curve are going to go up a full 1.1 on every single guy here. So add 1.1, add 1.1, add 1.1, and then subtract going in the other direction. Subtracted 1.1, subtracted 1.1, subtracted 1.1. It also includes the percent of the population that falls in each section. So typically the ones that we want to use are remembering that between +1 and -1 standard deviations is roughly 68% of the population. And then between here and here is going to be 95% of the population. And between here and here is 99.7% of the population. However, it's also sometimes useful to start from the left and move right, because that's going to be what a percentile is. So the percentiles are going to be a little different. I'm running out of room here, so I'm just going to go ahead and start writing the 2.1, the 3.2, the 4.3, 5.4, 6.5, 7.6, 8.7. And you can memorize these values, or you can simply use a calculator as I'm about to show. But as you move from left to right, the percentile, the total area under the curve from -infinity up to this point, is going to be 0.15, and then 2.5, and then 16, and then 50. Please note this 50 is a very obvious number. 50% falls in the left half, 50% on the right half. After that, it's 84, and you can see the difference here is 68, 97.5, and 99.85. And these are all percentages here. Percents. And these are the values, the weights of these chihuahuas. So what falls between what two weights and the 95% of chihuahuas? Well, we just marked that up. 3.2 all the way to 7.6. What weight marks the 16th percentile? Two ways to do this question. Way number one is memorizing that from the left-hand side up to here is 16%, or the middle 68% means that these two are 32%, meaning this guy is 16%. So this guy has to be 4.3. But we could have also simply used our calculator. Our calculator does percentiles for us. Anytime you want to use the calculator for percentiles, you're going to want to use the inverse norm feature. So the inverse norm feature does this. You're going to hit seconds vars, scroll down to inverse norm. The area in question is 0.16. That stands for 16%. The mean in this question was given to us as 5.4, standard deviation of 1.1. And then you go ahead and paste that guy up. And you usually see you will get the same 4.3 answer. No difference. Use the calculator. Don't. That's up to you. If a chihuahua weighs 88.7 pounds, what percentile is it in? Well, just looking at our graph here that we did, it goes up to 99.85% from the left-hand side. That's what a percentile means. But instead, maybe you'd like to use a calculator. You don't want to have to deal with that memorization. So previously, we were given a percent, and we wanted to find a value. We used the inverse norm. We used the regular old normal CDF. Oh, I'm sorry, I didn't explain that. You hit second, vars, normal CDF, and this is going to be the screen you're going to want to be at for the percentile to find that percent. So again, if you're finding a percent, normal CDF. If you're given a percent, you're finding a value, inverse norm. The lower value for all percentiles is -infinity. So we're going to write -99999. Please note, you could have actually just used 0 here because chihuahuas can't weigh less than 0 pounds, but I like using -infinity whenever possible here. The upper bound is going to be 8.7. The mean, just like before, 5.4, standard deviation, 1.1. Hit enter, enter, and you're going to get 99.86. If you notice, it's slightly different than this 99.85. The calculator's answer is the real answer here, so you kind of should have answered this 99.87%, but I will accept either answer on the test. I don't care which one you pick. What are the chances that a chihuahua will weigh between 3.2 and 7.6 pounds? Exactly the same thing as a normal CDF, or you could have simply added up the numbers as is appropriate. It'll be the 3.2 to 76. Well, actually, you just did this. It's going to be 95%. But again, you could have used a calculator to get the actual answer. Oh no, I haven't been showing you guys the calculator here. second vars, normal CDF. In the normal CDF, you're going to want to go between 3.2 and 7.6. Same standard deviations. And you will again get this 95%. And the calculator does give the real answer, 95.44%. But either way is cool. So if a Chihuahua weighs 2.1 pounds, what percent of Chihuahuas will be smaller? Well, it weighs 2.1 pounds. It's going to be over here. That's that 0.15%. Which means the other side is the 99.85%. And again, we could have used the calculator instead. If you used the calculator, you would have gotten 0.13% and 99.87% instead. If you were to randomly select 150 Chihuahuas, how many would you expect to be less than 6.5 pounds? So 6.5 up here, that's 84% of the situation. Again, you could have used the calculator for this, and I'm going to show that calculator move one more time. So doing it in the calculator again, you're going to hit second vars, normal CDF, and you want less than 6.5 pounds. So again, negative infinity all the way up to 6.5 pounds. And hopefully we get this 84 answer. We do, 84%. Simply multiply that 0.84 number by the 150, and you will get the number of Chihuahuas, 126.2. Please don't answer with the 0.2 Chihuahuas. That makes me sad. I don't want to imagine what 2/10 of a Chihuahua is. That's going to be 126 Chihuahuas. Okay, going on to the next page. So the next page here, they actually ask you to give us the two different situations here. So if you remember from the previous page, our standard deviation was going to be, our mean here was 5.4 for the Chihuahuas, and this is for the Chihuahuas, and the standard deviation was 1.1. And here they're giving the average weight of 7.5, and normally distributed with standard deviation of 1.5. So there's our mu, and there's our standard deviation. We got to draw both. For me, the most important idea here is you put the top value at the correct point. So the top value of the Chihuahuas is at 5.4. So 5.4 is going to be about right here. Then 1.1 to the left, which we did earlier is 4.3, is going to be where the graph goes from happy to frowny. So there we go. And from 1.1 above, 6.5 right here. So again, this is the unhappy part of the graph. And then the happy part happens afterwards. That's good enough for me. Uh-oh, my pen seems to be not working well there. And again, right there in the middle is this 5.4. Great. The other one has a mean of 7.5, so its tallest point is at 7.5. And it's a little bit more spread out. So you're going to be spread out more. Because you're spread out more, it's actually going to start a little bit lower. You don't really need to know that, but 7.5 is going to start a little bit lower. It's more spread out, so it goes up, down to 9 is where the unhappy part ends, and down to 6 is where this unhappy part ends. And again, it's a little bit more spread out, so you kind of go more so and more so. Honestly, that was a really terrible drawing. It really should have been more like this. But, whatever, you get the point. It's a normal distribution. It wants you to go ahead and label all the 99%, all this stuff. I trust you guys being able to do that. It's exactly the same as this previous page. Don't really need to do too much more, so I'm just going to not do that. Moving on to z-score. What does it mean for value in a set of data to have a z-score of 2? That means standard deviation. I'm going to write this. Standard deviation. Two standard deviations, two standard deviations above the mean. So back to our little Chihuahuas example, I'm turning it back over. We would say that 7.6 here has a z-score of 2 because it is two standard deviations above the middle value. I didn't use complete sentences, whatever. Find the z-score that has a value of 15 units below the mean. So if it's 15 units below the mean and standard deviation is 5, how many does it take to go from 15 down to 5? Well, that's 15 divided by 3, and that's going to be 15 divided by 5, sorry, I got ahead of myself. The answer is 3. But it's below the mean, so you want negative 3. 20 units above the mean. 20 divided by 5 is 4 units above the mean. 2.5 units above the mean. Well, 2.5 is half of 5, and it's below, so negative 1/2. Again, that idea is 2.5 divided by 5. If the value has a z-score of 3, how many units is it above the mean? Well, that means that it is 3 standard deviations above the mean. 3 standard deviations above the mean, if it's 5, is going to be 15 units. Kind of the same question as the letter A right there. If the value is in the 20th percentile, what is its z-score? For this question, you must use a calculator or a table. The calculator is far easier to do. What you are actually doing before we start, we talked about earlier how this is 16% all the way down here at the bottom. However, that does not quite give the full picture. That 16% all the way at the bottom goes up to right here is 20%, in other words, about right there. So it's a little bit more than, 1 standard deviation, but less than 0 standard deviation. So we're expecting an answer about negative 0.75 maybe. That's kind of what we're asking when we're asking a z-score 20th percentile. What is this number right here in terms of the z value? That's what we're asking. So to do this in the calculator, it's actually very fast. We use that inverse norm again. If you are given the percent, given the percentile, you're going to use the inverse norm. Second, vars, inverse norm. The area in this question is 0.20 because it is 20%. You could have just done 0.2. You leave your mean and your standard deviation alone. Those are the mean and standard deviations for a z-score. And sure enough, I said negative 0.75. I was close. Negative 0.84 is the actual correct answer here. Again, all in the calculator. So number 7, state the z-score and percentile. So z-score is going to be different than percentile. Percentile, calculator. Z-score, kind of just do it by hand. So z-score is always calculated in the same fashion. It is going to be the value minus the mean or average divided by the standard deviation. You could shorthand this using the symbols x minus mu divided by the standard deviation. So calculating this for the Chihuahua, we're going to be talking about z equal to 6 minus the Chihuahuas, which is 5.4, divided by 1.1. Definitely need a calculator for this guy. Actually, maybe not. 0.54 repeating, right? Minus 5.4 divided by 1.1. Oh man, I'm so good. 0.54 repeating. All right, the other guy here, z-score for toy poodle. Again, 6 minus, and then standard. This was 7.5 over 1.5, so this guy's exactly negative 1. And again, we can use a calculator to find these values. We're going to go ahead for the percentile. So percentile, if you're looking for a percent, you're looking for a percentile, you're going to use the normal CDF. Second, vars, normal CDF. Percentile always has negative 9999. The upper bound in this problem is going to be the value you're looking for, 6. The mean, 5.4 for the Chihuahua, 1.1 for that Chihuahua standard deviation. Turns out this is going to be the 71st percentile. So this is 71st percentile. This guy down here, you're going to use the same process in the calculator. Second, vars, do it again. Inverse norm, area is going to be, what am I talking about? Second vars, normal CDF. I don't know why I hit the wrong button there. Negative 999. The upper bound is 6. Standard deviation was 7.5. 1.5 for these poodles. And you get, we're just going to go ahead and say the 16th percentile. Question says, use the information to compare the probability of the Chihuahua at less than 6 pounds versus the probability the toy poodle is more than 6 pounds. This number is the less than 6 pounds for the Chihuahua. So this guy here is the 71%. But more than 6 pounds is 84% because these percentages must add to 100. So 16 and 84 adding to 100%. 84%. This toy poodle has a higher probability of being more than 6 pounds by comparison to the 71% probability for the Chihuahuas. Moving on to this next page here. So, did I skip a problem? No. Mean weight of a Pop Fizz can soda is 8 ounces with a standard deviation of 0.015 ounces is normally distributed. What is the z-score of a can of Pop Fizz grape soda that weighs 8.02 ounces? So our z-score, the value minus the average divided by standard deviation, 0.015. What is this value? Well, it's going to be 0.02, that difference there. How many values you are away from the middle, divided by how many standard deviations you are away from the middle. It's going to be 1.3 repeating. What does the square represent? Again, I'm not going to write it down, but what does it say? It says that you are 1.3 standard deviations above the middle value. Slightly unusual, in other words, but not that unusual. How many standard deviations below the mean is a can that weighs 7.954 ounces? So you need to figure out, first of all, how far away from the mean are you? Well, you're 7.954 minus 8, just like we do our regular change questions, and that's going to be 0.046 in the negative. So that's how many values you are away. But how many standard deviations away are you? You're going to have to divide that guy by 0.0015. And that's going to be just barely to the left of 3. I'm guessing negative 3.1, but I'm going to go ahead and use my calculator for this guy. I was right, negative 3.1. Boom. All right, so negative 3.1. And what percent of cans is less than this weight? Again, looking for that percentage, you're going to use that normal CDF. So second vars, normal CDF. We want to do the lower, less than this weight. So there, all the way up to the actual value, 7.954. And the average was 8. And the standard deviation was 0.015. Boom, boom, boom. And we get basically none of them. 0.1%. If you're having struggles with that, maybe you want to go 0.11% even. Just multiply by 100 and you'll get the percentage there, 0.11. Not too bad. What is the weight and z-score of a can that is 0.025 above the mean? Well, if you're 0.025 above the mean is 8, you must be 8.025. Easy enough. Using your normal z-score formula, you're going to get that minus 8 divided by this z-score 0.015. Please note, you actually didn't need to do that part. You could have just done 0.025 divided by 0.015. Maybe think about why that's true. Regardless, you're going to get 1.6 repeating. What percent of cans have a weight that is more than this? So you're trying to do more than that. You got to be really careful. You do need to use the CDF again, but this time on your normal CDF, because this is the lower value now, this 8.025, that lower value now, the upper value is now infinity instead of the lower being negative infinity. Again, the average here is 8. Oh, that was all the same. I didn't need to hit anything. And you're going to get about 5%. Maybe we can say 4.7%. 4.8%. I can round. Easy enough. If a can of soda is in the 30th percentile, what is its approximate z-score and how much does it weigh? So this is a two-part problem. So 30th percentile, we're going to use inverse norm. And we want 30th percentile. Well, if you want to find the z-score, you literally just type this in and then hit enter. Boom. You don't have to change anything. 0 to 1, so its z-score is negative 0.52. But if you want the actual value, again, inverse norm. And now your mean is 8 and your standard deviation is 0.015. And you're going to get this weight of 7.992 maybe ounces is the actual weight of that situation. So in a batch of 300 cans, how many we expect to be less than this? We're looking for a percentage first. We're going to multiply that percentage by 300. So we're going to hit second distribution, the normal CDF button. We're trying to do less than 6.05, so negative infinity, all the way up to 7.9685. Mu is 8, standard deviation 0.015. And we get this percentage. So the percent is approximately 1.79%. But we got to take that value and multiply it by 300. And we're going to get a nice equal to 5.36 cans. So why don't we just answer between 5 and 6 cans? 5 to 6 cans. That's a more reasonable way to answer this question. Problem number 9. For the following, considering the z-scores are normally distributed population, show the percentiles associated with each z-score to find your answer. What percent of the population is less than 1.5 standard deviations away from the mean? Shading the bell to represent. So 1.5 is going to be right here to right here. We're shading in this part right here. To do this, though, again, 100% calculator, second VARs, normal CDF. The lower is negative 1.5 because you're 1.5 standard deviations below and 1.5 standard deviations above. Mu 0, standard deviation 1. Paste this answer here, and we're going to get a 0.866 multiplied by 100 for the percentage, 86.6%. What percent of the population is more than 5.5 standard deviations away from the mean? Ooh, this is interesting. So it's 0.5 away, so we got to figure out what this value is, but then actually subtract it from 100 because we need all of this. The calculator can't really do that, so the calculator is only able to find the middle. So we're going to do 100% minus that value in the middle. Normal CDF. This time it's negative 0.5 up to positive 0.5. We get that number, multiplied by 100 to get the percent, and like I said, we are subtracting 100% because this middle part is 38%. So the remainder of it, must be 61.7%. All right. Margin of error. This question's so easy. Given the margin of error is 4.5%, given interval is likely to contain, this is actually crap. It is not likely to contain. It is reasonable to believe that it contains, but it's not likely to contain. That's a terrible way of wording it. Just really awful. 45 plus 4.5 is going to give us 49.5. That's all I did was added the 4.5 to this guy. Then you also subtract 4.5 from that guy. That's all margin of error is. Addition and subtraction. Easy enough. You get 40.5 to 49.5% of the population. Not of the population. One between those two numbers. It is reasonable to believe that the actual number of high school students that drive their own car to school is that. I don't know if it's really that high, but there it is. I guess I didn't show that in the calculator. I'm sorry if I took that to me. My bad. All right. Continuing on to the last page here, it looks like. In a random survey of 850 eligible voters between 18 and 25, 289 voted in the last election. Given the margin of error is 3.4%, well, we actually have to figure out what the actual percentage is. That's 289 divided by 850. 34%. Multiply by 100 to get us into percentages. Then you have to add 3.4 and also subtract 3.4. And you're going to get a nice 30.6 to 37.4%. And again, it is not likely to contain. This is wrong. It is not true. It is reasonable to believe that it's going to contain. Mean and standard deviation, margin of error is 3 minutes. Honestly, this question is terrible, so we're just going to cross it off and not do it. Great. Skip it. Okay, 13. A consumer group tested 75 randomly selected bicycle tires. Given a margin of error is 4.4 miles. We don't need to do more margin of error. The margin of error questions are going to be like this in the test. They're going to be nice and simple, so don't worry about these ones. Sample proportion, that's the 435 over 185. I don't even think we need to do the ending of this. But what I do want to do is do a last-minute little lesson of something that's guaranteed to be on this test that might not have been reviewed in this review packet, but hopefully your teacher talked about this in class. Not all distributions are normally distributed. There can be other types of distributions. For instance, a distribution that looks like this, we call this a right skew because the right-hand tail is really large. Likewise, you might have what is called a left skew because this left tail is really large. And you might also have what is called uniform. A uniform distribution is just flat the whole way through. This is called uniform. If you end up taking statistics or even a biology class, you find other distributions such as the chi-square distribution or the t distribution or the f distribution or a whole bunch of other distributions that are possible, but these are the only ones we're going to be dealing with are right skew, left skew, and uniform. Please note, when you see a question like this, you cannot use any of the normal distribution rules. You must start going from the definition of percentile. So for instance, if I marked this up and said this was 3% and this was 7% and this was 18%, and I want to know what that value is at, I have to do 3 plus 7 plus 18, and that's going to get me a nice little 28 percentile. Anyways, hopefully the video was interesting. Good luck on that test either Monday or Tuesday next week, guys.